Welcome, everybody. My name is Vuk Radovic, and today I will be talking about artificial intelligence, machine learning, and deep learning. So, who is this talk for? This talk is for you guys in the business community. This is not talk for IT professionals or AI practitioners. So, if you know nothing about these topics, I will try to bring it to you. First, we're going to go over some terminology. So when people talk about these things, you know what they're actually talking about. Second, we will go over the types of problems that AI is trying to solve. We're going to go over some different approaches to problem solving in machine learning. And at the end, how you can apply this in your line of business. If you walk out of here with some ideas of what you want to try to make things better in your business, I will be very happy. So let's go over the terminology. Artificial intelligence is the theory and development of computer systems that are able to perform tasks that normally require human intelligence. So basically anything in computer science that tries to mimic intelligent behavior is under the realm of artificial intelligence. Machine learning is a subset of artificial intelligence, and that is trying to provide systems the ability to automatically learn and improve from experience without being explicitly programmed. And this, without being specifically programmed, is actually very important here. And I will go over this in the next slide. And finally, deep learning, or deep artificial neural networks, is a special approach to machine learning where you're using artificial neural networks that resemble the brain infrastructure. And we are trying to deploy that infrastructure and mimic a real learning. So now, one of the most important things to understand about machine learning is its difference from traditional programming. In traditional programmer, the programmers are explicitly programming logical constructs. So basically, if you do this, then you do that. If you have this information, do that. If the user does this, you respond by showing that. So that's traditional programming. Machine learning is a completely new paradigm. So the way you work with machine learning is that you gather the data. After you do that, you pick the machine learning algorithm or infrastructure, you set some parameters, and you let the model train on the data. And after the model is trained, what comes out of the other end is some kind of intelligence. Now, you can test how good that intelligence that comes out of the other end is. And if it's not good, you can repeat the process, maybe clean the data, maybe tune the algorithms, or maybe change the algorithm and then get a new model that has maybe improved intelligence. But important point here is that you're not programming that intelligence. That intelligence is being derived by itself using certain mechanisms. Okay, let me go over some history briefly with artificial intelligence. In 1943, we had the first mathematical model of neural networks. 1956, artificial intelligence term was first coined in a conference. Then 1957, we have some foundation that is being set by Frank Rosenblatt for deep learning, deep neural networks. In 65, we've seen the first prototype of artificial neural networks. So now, after the initial hype, when there was no real viable results, people lost interests and governments stopped funding. Then in the 80s, interest picked up again and dropped off again because realistically nothing really great was being produced as far as a product. Now, that actually changed in 1997 when Deep Blue became the first computer to beat world chess champion Garry Kasparov, and that was a very important milestone. Now, in 2010s, basically, it started rapidly picking up steam and is really today becoming part of the mainstream and part of our life. So artificial intelligence, machine learning is really affecting our life today. Now, you may ask yourself, why now? Why not in the 60s, 70s, 80s, 90s? Why all of a sudden we're seeing some breakthroughs? Well, first of all, the processor speed. Deep learning, actually machine learning and deep learning models, they need a lot of processing power. If you don't have processing power, you cannot really do much with machine learning. So what has helped is this exponential growth of processing power. Just to give you some example, the Apollo guidance computer that actually put the man on the moon had 64 kilobytes of memory, worked on 0.04 megahertz, while cell phones today are 20 times more powerful. So basically what you have in your pocket is 20 times more powerful than the huge computers that put the man on the moon. And the other part of this revolution is processor parallelization. That means that we are now deploying more processors to do the work that was being done by one, and we are dividing this work and sometimes into 1,000 and 2,000 processors. What also helped is the GPU video cards that are built for graphics, because powerful graphics need a lot of processing power. So people invented those GPU cards that actually have thousands or 2,000 processors within the card. And this also fueled some of the revolution in artificial intelligence. The second reason is the data. Data is the fuel of any machine learning because machine learning works on data. If you have no data, you cannot have machine learning. And the more data you have, the better models you can build. So in combination of storage costs being extremely cheap and extremely powerful, basically following the same pattern as the processor power, all of a sudden, with the internet revolution and the revolution of smartphones, we have enormous amount of data that is being generated. This data is in texts, in sounds, in pictures, in videos, Twitter feeds, metrics. The amount is just staggering. Okay, let's try to categorize machine learning by the problem types that it's trying to solve. So there are three main problem types that are being addressed by machine learning. And the first one is supervised learning. In this case, based on a set of features, machine model builds some type of prediction of the desired outcome. In unsupervised learning, is also based on a set of features, except for this time we're not asking the model to predict anything, but we're asking the model to try to find some kind of a clustering or logical grouping of this data. And finally, reinforcement learning is where model is actively participating in the problem. So this is basically the cases of games where the model is participating and playing the game and learning how its behavior is actually affecting the outcome. So In supervised learning, the best thing is to go over a real example. So in this example, let's say your great grandma left you an apartment in Belgrade. And now you're deciding that you don't want to keep it, you just want to sell it. So if you don't want to get a real estate agent and you don't trust people to tell you what the price is, the most common thing would be that a reasonable person would try to find out what is the reasonable price that this apartment can be sold. So in this case, you have gathered all this information about all these apartments and houses being sold in Belgrade, and you want to deduce some kind of intelligence. Now you're looking at the square footage, you're looking at the number of bedrooms, bathrooms, you're looking at the neighborhood, maybe if it has a balcony, maybe when it was built, and you try to figure out what is the effect of those characteristics and which one of those characteristics is really driving the price. So this is the exact type of problem that supervised learning is trying to solve. You have a lot of data, you have some characteristics for each data, and you have the outcome variable, which is the price that is being sold. Now, you plug all this into a machine learning model, and you are basically expecting a formula or some kind of a intelligence to come out of the other end. They will tell you, based on the data, what is the price that you can expect. So let's say our supervised machine learning model will look at 35,000 properties sold in Belgrade in the past year and give us some kind of complex formula that best defines the relationship between driving characteristics and the output variable. So at the end, that supervised model will actually tell us that your house or your apartment is worth 103.5 thousand euros. Now, the model may actually decide that maybe the area of the apartment is the most important characteristic. Some of the other characteristics are bedrooms and bathrooms, and the neighborhood is important, but it may also decide that everything else is kind of meaningless, and we are not going to use this as a driver of the price. So here are some other good examples of supervised machine learning. Let's say you want to calculate the churn rate. Churn rate, if you're like in banking or insurance, you have millions of customers. These customers are actually occasionally, closing their accounts, going to your competitors. So you want to derive some intelligence is who is actually the customer that is likely to leave you and who is the customer that is likely to stay. So if you have that data for the past maybe couple of years, you can enter some characteristics of your customer like age, marital status, salary, employment status, profession, whatever you can gather on that person. And then you also have the information if they have closed the account or not. You can plug this into a supervised learning model, and it can, if you have a lot of data and if you train this model well, you can come up with a reasonable model that will tell you, okay, what are the customers that are having a high probability that they're going to leave you, and what are the customers that are probably not going to leave you. So you may want to address this in your business decisions. The other example is handwritten digits. For example, if we have a picture file as a matrix of pixels of handwritten numbers, we want the machine to automatically start recognizing the digits. And so the characteristics is a picture, but more granular characteristics are actually the pixels that you give it. So it's a large set of pixels, And the outcome variable is you want to guess what is the digit. So that's another example of supervised machine learning. You have the characteristics, you want the model to come up with some kind of prediction that makes sense. Also in agriculture, let's say you are interested in maximizing your yield, but you don't know which characteristics are really affecting it to what level. So if you have a lot of data about your soil, you can have all the elements, in that data set, or the average temperature for maybe each day during the growth of your crop, the average rainfall, number of pesticides, herbicide used. You can actually train your model to tell you, what are the things that you can do, you can improve, what are things that you need to pay attention to, and what are things that you can actually ignore. Another good example is hacking attack, like in networking, when you have a lot of events happening in your network, and sometimes you're under the attack, other times you're not. So what you can do is plug in all this information about your system when you were under the attack. Also plug the cases when you're not under the attack. You can have the computer learn and say, this is actually what is happening under the attack. Or you can just say, if in everyday monitoring of your network, you can have the model say, hey, you may be under a hack attack now. That was supervised learning. So in supervised learning, obviously you have characteristics and you have the variable that you want to predict, or you want your model to predict. In unsupervised learning, you do have a lot of data, but you don't want to predict a variable that it comes out. All you want to do is have your model group or cluster the data. So for example, the most common case in unsupervised learning is examples of iris flower. When botanists gathered all these iris flowers and put some petal width, sepal length, and petal length into the clustering algorithm, came up with the 3 different types of, or subtypes of this flower. So now we know that iris flowers are grouped into 3 different subgroups. And you may ask yourself, like, so why is it important? Who cares? Well, I will give you another example where you can actually see the commercial value of this clustering. So for example, let's take a look at the songs that are being listened to by a certain individual. And let's say this individual is, we plot all the songs that this individual is listening to into a 2-dimensional space, just so we can visualize it better, although this dimensionality can be 3, 4, 5, it can be 100. So in this case, let's say we are plotting the prevalence of major or minor chords in the x-axis, and the rhythm, how fast the song is, and we're trying to predict if this person is having some tastes clustered in different areas. And we may find out that this person likes blues, and he also likes Serbian folk music. So you can see that all these blues songs are in the lower left corner because it's all major chords, and the rhythm is quite slow, while the Serbian folk songs are somewhere in the upper right area with much more minor chords and a little bit of a livelier rhythm, right? So now the model is realizing, okay, this person is listening to these 2 types of music, and if I want to suggest some of the music for this person to buy, I don't want to take the average of all these songs. I'm understanding that this person is listening to music in certain clusters, so I will be very happy to get suggestions like B.B. King or Dragana Mirković songs. So you can see how much of a commercial value this can be. So some of the other unsupervised learning examples is Netflix movie recommendations, Amazon recommendations of books or the products that you need to buy, at Spotify, suggested songs that I just described. Finally, reinforcement learning is unlike supervised and unsupervised learning in a way that supervised and unsupervised learning are actually observing the data as is, and the data is not changing. And based on this not changing data, we are coming up with some kind of intelligence. With reinforcement learning, some action is being taken by the model. So the model is actually actively participating in this field that is trying to examine. So that action that model takes implies some short-term and long-term award or punishment for the model. But the important part is that action is also changing the playing field. The action that the model takes also changes the playing field, which means it changes the data. And the goal here is not to predict a variable or to cluster the data. The goal here is to come up with some kind of intelligent strategy or how to play the game. This is one of the most exciting parts of machine learning, and today it's being used in self-driving cars. Obviously, in self-driving cars, you have a driver there that operates the car, so the actions taken by the driver is also affecting the situation on the road and the things that we're seeing. In robotics, like a lot of the things where robots are learning to handle objects, it's also based on reinforcement learning. And also this whole thing started by another big milestone where Google's DeepMind actually beat the world champion in this game called Go. And this is actually what brought this reinforcement learning ideas to us. It's also in the video games, applied in video games, and some of the models, computer reinforcement learning models are being trained, actually learn how to play the game without being explicitly programmed. So in this slide, I'm just going to leave you a little bit of a recap of the three different types, some of the explanations. You can use this as a reference. Now we can categorize machine learning also by methodology. In algorithms-based machine learning, we have well-defined algorithms that are based on statistics and they are applied to solve the problem. So most of them are borrowed from mathematics and statistics, like linear regression, logistic regression. They are tunable, so you can change the parameters, but you basically understand, what is the approach that machine is taking to learn. The other one is artificial neural networks or deep learning, which actually does not have a specifically defined algorithm, but we have an infrastructure of these artificial neurons, and is based on a network of cells. They're designed to mimic neurons and to mimic the behavior of a real brain. So I'm going to get deeper into this. But first, let me just mention some of the important machine learning algorithms that are in use today. As we said, with supervised learning, we have two types. One is where we classify the data into yes or no, or into a set of digits, or recognizing a picture, or we have a regression where we actually try to find out some real number like yield or a price of the apartment. So in this case, we have support vector machines, naive Bayes, nearest neighbor are the most common ones, also have linear regression, decision trees. And in unsupervised learning in the clustering world, the most common one is k-means. Now to the exciting part, the neural networks and the deep learning. This is basically what is fueling the revolution today. This is where computer science meets neurology. So this is all motivated by how we think and how is our brain designed. Now, when you look at a single neuron, it basically has dendrites that is picking up some impulses, and the neuron itself has some logic in it to, based on those inputs, to have some kind of output that goes through the axon and goes on to the next neuron. Now, to model this single neuron is really not that difficult. It's basically how every computer program works. You have some inputs and you have some logic and you have some output. Now, the process of learning is actually not about neurons themselves. The process of learning is about the network or neurons that communicate together, store the information, and tries to understand and create some kind of a system, learned system of optimized behavior. So now the question is, can we emulate the process? We could always emulate the neuron. This is very simple, but to emulate human brain, which has 100 billion neurons that are connected together, is a very difficult task, and it's difficult because, again, you need enormous amount of processing power. But right now we are at the point where we can do that. So the deep neural networks are looking something like this. So we have an input layer that is actually accepting the data. This is where the input data comes in. We have an output layer that is showing us the predicted variable. And we have this brain-like networking structure of neurons in multiple layers whose goal is to interpret this data and to come up with the best model to export the correct predicted variable. So just like a little child in the beginning, he knows nothing, but as it's seeing, one set of data, one set of characteristics coming in and a desired outcome, this internal neurons are starting to adjust their weights. Now, when we feed in, for example, in our real estate problem, in this input layer, we're feeding these characteristics. So let's say this red one on top is the neighborhood. The next one is the square footage. The third one is number of bedrooms. Next one is number of bathrooms, etc. At the end, we have the price that this apartment sold for. And now when we start feeding this data, like 1,000, 2,000, 40,000, this internal neurons are going to represent the weights, and these weights are going to slowly shift and adjust to the point that at the end, when we have passed 30 or 40,000 data units, they are going to be trained well enough to understand and predict the price. There are certain other parts of deep learning network. So, for example, convolutional neural network are designed a little different here, and they are generally used for processing and recognition of pictures, recognition of faces, handwritten digits. So the challenge here is that your input space are pixels, which sometimes are counting in millions. So when you have millions of pixels, coming in as characteristics, you have to make that network a little less connected, because we don't want millions of neurons connecting, every neuron connecting to every other neuron in the second layer, and so forth and so on. This would be computationally be very expensive. So the idea here is that certain areas of pictures are kind of processed in a separate way in the first layers of this network, and they're further down the line they're being put together. So in generally, in the first layer, you are kind of trying to recognize certain shapes. The second layer, those shapes are being connected, and you're starting to recognize certain features like a nose or a mouth or an eye. And at the end, you connect all the pieces together, and you can recognize that if this is a person or who that person is in the case of facial recognitions. Another important variation of neural networks is recurrent neural networks. So this is very important in certain problem spaces where the sequence is very important. So for example, in natural language processing, when we speak in sentences, every word is kind of dependent on the preceding words to understand the overall meaning. So words are not individuals, in a way that what they represent. So because the sequence is important here, some of those hidden layers are actually have a feedback loop to themselves. And the reason for that is that whatever happened previously needs to be remembered to get the correct meaning. This is very prevalent in natural language processing, in language translation, in music. For example, with notes, a note does not mean much unless it is connected to the other notes. And this is basically the beauty of music is the sequence of notes, not the notes themselves. Deep learning is also being applied in reinforcement learning. So, but the best way to understand this is I'm going to play this video right now, and you can see in this video that computers trying to learn how to play Pac-Man. Now, important thing to know is that nobody has programmed computer in a way to say, this is a Pac-Man, these creatures are here trying to catch you. You're supposed to eat those little, pieces. You're supposed to clean the board and blah, blah, blah. So you're not programming anything. You're just letting the model learn. So as you see in the beginning, just randomly does things and figures out that certain rules of the game and how to maximize his behavior. And after certain number of tries, just like a child has learned, basically how this game functions, and the most important thing is, the most fascinating thing is that at the end, it just clears the board and plays almost better than a human. So this is very interesting, and I'm just trying to point out here that reinforcement learning are also being done in the space of neural networks. Okay, so let's have some fun now. Here is the list of celebrities, and let's play a little game. So whoever recognizes a celebrity first wins. Okay, go guys. Can you recognize any of them? Seriously, I can't believe you cannot recognize a single celebrity. It's like you're not watching television, or you're not following the news. What is the problem here? Well, the problem here is that these are not real celebrities. Actually, these are not even real people. And what is happening here is that computer is generating a machine learning model of deep adversarial networks called generative adversarial networks is generating these faces. So what we have fed this model is a big list of faces of celebrities, and we have asked the model to create some new faces that will follow the pattern of celebrities. Well, let's talk about generative adversarial networks. Is one of the most fascinating and frightening advances in deep learning. As you can see, some completely random faces that look totally real can be generated. Some people have also trained models to do the impressionist paintings. So these paintings are indistinguishable from the works of Monet, Chagall. There are some other ones who are playing with the composed music by Bach. Bach was very, what is the word? He composed a lot of music. So because he composed a lot of music, we have a lot of data. And some people had plugged this data into generative adversarial networks. And we have compositions entirely composed by the machine learning models that sound pretty much entirely like Bach, to the point that regular people cannot recognize the difference. Now, a couple of other frightening ones is that we can now generate videos with the real people speaking with fake speech. Basically, you can implant the speech and have them speak and have this being totally credible and believable. Deep fakes is basically you can have actors act in movies without actually having them doing the acting for real. We also have like models write poems, songs, music, screenplays. So now let's talk about this. Who has the competitive advantage in AI? Well, somebody said somewhere that whatever was oil in the 20th century, it's going to be the data in the 21st century, which is entirely true. So who has the power to benefit from this revolution? Those who have the most data and those who have the most processing power. Four biggest players come to mind: Amazon, Google, Microsoft, Facebook, maybe Apple as well. I can also add here some governments. Governments generally do not own the data, but they can get the data. They have power to pretty much walk in to Google or Microsoft and force them to hand over the data. And this is something very important to know, that big governments like United States, China, Russia are paying very close attention to artificial intelligence and can probably become big players in this space. Now, let's talk about some issues and implications of what is happening with deep learning. One of the biggest problems with deep learning is complete lack of control about the model's outcome. That, as I said before, these models are not explicitly programmed, especially in deep learning model where you just have a neural network trying to figure out some things from the data. And if the model figures out things that are not really something that you want, you can really not fix it. You can only discard the model, or you can train another model or change the parameters. But if model is coming up with some kind of outcome that you don't like, then you really cannot do anything about it. So also it's becoming very large potential for abuses. For example, insurance companies can abuse the knowledge and discriminate, based on gender, ethnicity, maybe some other completely random characteristics. Like, for example, they can find out that tall people with glasses and short hair are really bad drivers, and raise my rates. The other thing is with the generative adversarial networks is rogue entities can generate fake news. They can generate fake people, fake views at a massive scale, So think about an entity that creates maybe 20 million people on LinkedIn with fake faces, fake biographies, fake CVs, fake everything, that that could be, problematic and change the way we view internet, and we trust some of the things in internet today. Fake films and audio featuring real people can really destroy people's lives, So finally, what does the future hold? This is now here is just an opinion, but I think we can all agree that eventually most jobs as we know today will become obsolete. For example, self-driving cars, trucks, planes are going to have a lot of people lose their livelihood. But deep learning is also going to affect some of the more professional uh, areas of employment, like, for example, investment management, with the accounting, specifically now with medical imaging, we have machine learning models predict better than actual doctors. And obviously this can have a very large impact on society. So for example, what will most people do? How will they survive? Is it going to be another huge gap between those who have and those who have not, also based on those who can and those who cannot? And that threshold is what is employable can be much higher. And the other thing is, what will be the utility of human intelligence? If you remember the days with GPS, it was really important to know to find your way around. Now it's not the case anymore. You just plug in the GPS and you can have no idea of where you actually are as long as the GPS is taking you there. So a lot of things with these advances, we are also not getting smarter. I think kids in schools are not even learning how to multiply and divide numbers by hand. Taking a square root is all done by computers. The question is this going to affect us, and to what degree? Well, this is the end of my talk, so now we can take some questions and open it up for discussion. So, does anybody have anything to ask?